got through the first two pages, but then it was the third page that we needed to look at. And in particular, we had that there, piecewise defined function. So if we have a piecewise defined function, so g of x is equal to this. Okay, so what we want to do is, well, first off, where's the problem point that we need to kind of worry about? Probably. Well, yeah, like where might continuity even be a question? At the x value, not the y value. Yeah, it's 0. Okay. And because what happens if you plug in 0 to both of these things? Yeah, you get different answers, okay, which means it's not continuous at the given point, right? Because the left and the right-hand sided limits, what's the left-hand limit? Yeah, what's the left-hand limit? 6. What's the right-hand limit? 0. And last time I checked, those are not the same thing, okay? So if the limit doesn't exist, what is required for continuity? The limit of the function has to be the value of the function. And is that the case here? No. Okay. So this is not continuous at x equals 0. Now you might guess if it's not continuous, it can't have a derivative there either. But we don't actually know that yet, whether there's what the relationship is between continuity and differentiability. So let's look at what the derivative would be at 0. Well, it would be this. G prime of 0, sorry for that, is equal to the limit as h goes to 0 of g of 0 plus h minus g of 0 all over h. Okay, that's the definition of the derivative, right? Yeah? Okay. So if that's the definition of the derivative, we just now need to evaluate whether or not that limit exists. Ha, he made it. Welcome. It's great to see you. Um, so, yeah, so we need to ask, does this limit exist? Now, in order for us to do this, um, we have to be able to compute whatever g of 0 is. But what did we just establish a minute ago? Yeah, g of 0, well, actually, g of 0 is defined. Sorry, the limits were what was. So which of the two cases applies if g or if we're plugging in 0? The bottom one or the top one? The bottom because of the greater than or equal to, or sorry, less than or equal to. All right, so g of 0 is equal to 6, right? Okay, so that part's cool. But what is g of h? Well, what kind of quantity can h be? We want to think of it as being a really tiny quantity, but like throw out some numbers that it could be. Right, so what did h represent? We picked a point, and h represented how far away from that point we went. Okay, in the pictures, we always drew it going to the right of the point. But does h have to be a positive quantity? No. So we're thinking of it as being a tiny quantity that could be positive or negative. Okay? Now, if it could be positive and it could be negative, what's the issue with computing g of h? Look at our function. It has different definitions based on which side of 0 we're on, right? So if h is positive, which line do I look at? The top one. If h is negative, which one do I look at? Bottom one. Okay. And so what this means is the limit as h goes to 0 from the right of g of h, or sorry, g of h minus g of 0 all over h. We have to split this and do it as two limits, the right-handed one and the left-handed one. Okay? All right, so let's work out this one. What is g of h if h is approaching 0 from the right? That means h is positive numbers. Who's in charge in the function? Which line? Top one or bottom one? Top one, if h is positive. Yeah, wake up. Start drinking coffee. What do you have in the cup there? Mountain Dew or some water? Okay, yeah. Um, okay, so if I plug h into that top function, I get, what was it? H squared plus 2h. What did we say g of 0 was? 6? Yeah, it doesn't matter exactly because it's just the value, not the thing it's approaching. Okay, so I need to subtract that off. Okay, all over h. Okay, good. All right, so something interesting, well, maybe doesn't happen here that has happened before. Normally, when we got to this stage, what did we end up getting? Yeah, we were able to like do some factoring and, combine some terms and clean it up a little bit so that an H canceled from the bottom. Does that happen here? No. Okay. So what is the value of this limit? Does not exist. Okay, now let's make sure we're clear as to why it doesn't exist. Could I rewrite this as this? Okay, so if I just divide everything by the h, well, what's the problem then as h goes to 0 from the right? The first two terms are cool. I'm getting basically a division by 0, and there's no algebra that I can do to make this problem go away. Okay. Now, if this 6 were a 0, we'd be in business, but it ain't. Does that make sense? Yeah. Yeah. Okay. So g of h is this part. Okay. But also, if we're taking the limit as h goes to 0 from the right, what kinds of values is h assuming? Positive values. Okay. They're really teeny because we're approaching 0, but they're positive, which means I have to look up at the function and say, what are the values of the function if the input is a positive number? That's why I plugged it into that one. Okay. Now, we're about to turn around and do it from the negative side, in which case we'll plug into the other part, right? Okay, so this one-sided limit does not exist. Do we buy that? How many Bitcoin do I get for it? No? Huh? Oh, yeah, that's true. Um, how many of you guys watch the Super Bowl? Did anybody pull out their phone and scan the QR code? Uh, yeah, yeah. Well, there's that. Okay, here's the other way, because that wasn't the only like crypto related ad on the Super Bowl, right? So, like, I don't know if you guys saw the one from last year's Super Bowl with Matt Damon, right? So here's the fundamental question you have to ask yourself. How did they pay Matt Damon for doing that ad? Because if they didn't pay him in crypto, that tells you everything you need to know right there.
because of like the tax laws in LA, plus crypto being down right now, he only got paid $37,000 for this year. He owned that stuff.
Yeah.
Compared to like what would have been like 4 or 5 million had he just taken in regular tax.
Yeah. It's a great way to make money off of other stupid people. But yeah. Okay. So, now technically we could stop here, right? Because if this one-sided limit doesn't exist, does the limit have any hope of existing? No. Okay. But just for the sake of demonstration, let's do the left-handed limit also. Okay. So I need to consider the same thing, but this time from the left. Okay. And okay, what did we say g of 0 was? 6. Okay, so that part stays the same. But if h is approaching 0 from the left, h is now assuming on negative values. What was the function defined to be for negative values? The 2x plus 6. So that's why I'm going to put 2h plus 6 right there. Okay? Is that all right? Okay, good. So, now this one will, because what just so happens to happen with the 6s? Yeah, they happen to cancel. And because they cancel, the h's cancel. And what's the limit of a constant? That constant. Okay. So this one just so happened to work out. Okay. But what did we say? This limit and this limit, well, let me circle it this way, right? The D and E was the left-hand limit, or excuse me, the right-hand limit. The 2 was the left-hand limit. Are those the same thing? Nope. So what that means is, conclusion, the limit as h goes to 0 of g of 0 plus h minus g of 0 all over h does not exist. Hence, g is not differentiable at 0. Okay? So so this is a new definition, right? We defined what the derivative was in terms of a limit, right? Well, that limit could either work out or it doesn't. If it works out, great, that's the value of the derivative. If it doesn't work out, then the function is not differentiable. Okay, does that make sense? All right, so think of this in the same way that when we talked about continuity, continuity was defined in terms of a limit, right? And that limit could either work or it didn't. And so it was possible for a function to be continuous at a place or not continuous at that place. The derivative is kind of the same thing. The derivative can be continuous, or sorry, the derivative can exist at a place or it can't. Just depends on the function. Okay, so does that kind of make sense? Now, let's graph this thing and kind of see geometrically why the derivative doesn't actually exist. We've done it algebraically with all the stuff we just did, right? But let's look at the picture and see what sort of the, suss out what's going on. Okay, any questions on the papery stuff before I switch the screen over to Desmos? Speak now, forever hold your peace. I know some of you kind of have RBF going on. No? All right. So let's go back to our dear friend old Desmos. And it just so happens that we already had this one graphed, and where's the? Oh, here we go. All right, we wanted to graph this, of course, for x. What was it? Greater than 0 on this side. Oops, dang it. How do I make a right parenthesis? Oh, okay. There we go. Okay, so that's the blue one is the positive side, right? And then what was the other part? 2x plus 6. 2x plus 6. Oops. Need an x there. And that was valid for x less than or equal to 0, and then hit enter. Okay. So, what's sort of the problem? Yeah. Okay. So this one actually has no hope of being or excuse me, differentiable because it's also not continuous. We established that a minute ago. Okay. And it turns out, we'll talk more about this, that a function can't be differentiable if it isn't already continuous. That kind of makes sense just looking at a picture. Okay. And we'll actually prove that. It's not too hard to do later. But another way we can think of it would be, what are the slopes of the tangent lines on this side? 2, it's a straight line, so okay, that's easy. What about over here? Well, that thing's a parabola. Couldn't we use our little trick from Monday to maybe figure out what the slope ought to be there? Yeah, probably. Okay, but the problem is that they don't match up. Okay, now what would happen if I took this 2x plus 6 and I pulled off the plus 6 and slid it down so that this thing was continuous? Does that necessarily mean the derivative is going to exist? Not necessarily. Could, okay, but we're not sure. We'll have to go back and rework it basically. Okay, so let's do that. Let's take the plus 6 and just delete it. Okay, in which case our line will come to this point right there, which is exactly where the parabola ends. Okay, so is that all right? Yeah. Okay, so and we'll look at some more graphs as to there are lots of ways that a function can fail to be differentiable. Okay, you might look at this one and say, well, McKinney, this one doesn't really count because it's also not even continuous. So, like, you're cheating. Uh, so later, what we'll do is say, can we draw a function that's continuous but not differentiable? Okay, and it turns out, yes, we can find such functions, and they're actually pretty easy examples. Okay, so let's just change this to 2x, just 2x, and rework it. Okay. All right. So let me change the function, and I'll call it f this time. Okay. So it was this and that. Okay. All right. So as before, we need to compute two limits. Okay. We need to compute the limit as h goes to 0 from the right of f of 0 plus h minus f of 0 all over h. Okay. Now, why am I doing this at 0 plus h and f of 0? Because what's the point that I really am interested in right now? 0. Okay. The other points I'm less interested in. Okay. So I'm fixating my attention on 0. And now we need to do what we did before, which is if we're coming at, yeah, go ahead. Oh, yeah, it is. Thank you. Because otherwise the next step is going to be a problem. Okay. So let me just simplify this a little bit. Right? What is f of 0 now? Well, yeah, it's 0, right? And in this case, it happens to be that you get 0 no matter which one you plug it into, but which one should you plug it into? The bottom one. Okay. Okay, so, and if I plug H into this, which one should I plug H in? The top one. So I'd get 2H, so limit H goes to 0 of what? H squared plus 2H plus 0, sorry, minus 0. Not that that matters. All over H. Okay, so this looks exactly like it did before, except instead of minus 6, we now have minus 0. Okay? Okay, so now what happens this time? Yeah, what happens with these H's? I can factor one of them out on top and cancel it with the dude in the bottom, and so H squared plus 2H turns into H plus 2. And what's the limit of that? 2. Okay, that's cool. That's cool, Kyle. All right, so now what? We need to do the same thing from the other side. Okay, so I'll give you guys a second to scribble that down. Huh? Yeah, spoiler alert. It's also going to be 2. All right, so let me know when you've got this scribbled down so I'm ready to move on. Yeah, I do need to start handing the cups back out. Sorry. Actually, what I ought to do maybe this summer is like install a bunch of buttons at every chair and a bunch of LEDs.
Might as well do it. That was easy.
Yeah, we can make it like ultra multicolored. Like that's what we're gonna do. We're gonna RGB the absolute crap out of this room. Hey, yeah. And I could put in a disco ball and like when you're coming in, there's like EDM playing and yeah, that might be a little much. Well, this can be arranged, Jaden. Right. Um, the power is completely within your hands. So, yeah, that actually would be a pretty cool project to just RGB the crap out of it. And actually, with like some RF units and stuff, I could have like a master like panel here that had every seat's like a little map with your lights. Wouldn't that be cool? Oh, man. And then I could do the same thing, but it would be over in the bathrooms in the library, and so that you could look at it and instantly know whether or not there was a bathroom available and where in the library it was. Huh? No, oh, but it would be even better than the ones in Europe because it would also tell you every other bathroom in the entire building, right? Wouldn't that be cool? Yeah, exactly. Take that, Europe. Um, so, you know, you may have your socialized health care and, living wages and adequate public transportation and but we got lights. So yeah. Yeah, and actually interesting. I mean, has anybody ever been to Europe, right? France or Germany, right? The idea of a pay toilet was just fascinating. Now, that said, they were pristine, but like being like there was somebody whose job it was to be the bathroom attendant. And it's like, well, I mean, it's Europe, right? So I'm sure they made a decent amount of money, but like, I'm sorry, I would not want that job. I mean, if there's a definition of a shitty job, it's that. Yeah, literally. Okay. All right. So we need to do the same thing from the other side. Um, except this time, what is the function? 2x, and so it'll be 2h when we plug in h. Um, and this time, what happens? it becomes the limit of 2, and that equals 2. Okay, so this time we got the same value. Okay, all right, so what do we conclude? Okay, so we just found that that limit existed and was equal to 2 in this case. And so the conclusion is that f is differentiable at 0. And what is the value of the derivative at that point? 2. Okay, now from our graph, did that make sense? 2 seemed like a logical number because what was the slope there? 2. Okay, okay, good. Now, we could doctor this up and basically make other examples where the two pieces meet, but the answers are different. Okay, and we'll come back and talk about some of those a little bit more later. But yeah, for now, I think this is good. Okay, question, preguntas, fragen. No? All right, très bien. Okay, so let's look at the next one. Tangent lines. Well, what do you need to describe any line? You need two pieces of information, a slope and a point. Okay, that point could be the y-intercept, which is a particular kind of point, but you still need to know a point. Okay, so we need a point and a slope. Okay, all right, so let's look at number 4 there. F of x is 10 at x equals minus 3. Do we know the point? -3 comma something. Okay, do we know the y coordinate? Like, was that a given quantity? No, we had to figure it out. Okay, because if our x coordinate is given to be -3, then what's the y coordinate got to be? Whatever f of -3 is. What is f of -3 in this case? 10. It's a constant function. Okay, so there's no arithmetic to do. Okay, so that means that the point that we're interested in is at -3 comma 10. Okay, Gucci? We also need to know the slope. What gives us the slope? The derivative. Okay, so we need to compute the derivative at, that should be -3. We need to compute what is the derivative at -3. Okay, because that's the place we're interested in. Well, I could compute instead f prime of x and then just plug -3 into the answer. That's the better way to go. Okay. All right. So how do I compute this derivative? Well, what is f prime of x defined to be? That, right? Okay. It's the same thing as what we were using in the last example, except this time we're just letting x be x so that we're doing this sort of at every point. Okay, and we just got to figure out that limit. Seeing mystified looks. No. I have to say I hate the masks because I can't see what the hell, like, and I'm just waiting with bated breath until Feller's email that releases us from our servitude. Yes.
Ingram said they're like reevaluating it now.
Too bad we go on break and then we have to come back and put it back on.
Yeah, I know.
At least they can go without masks to the Super Bowl. All of them in LA. Hey, we're safe.
Yeah, I'm so over this.
You said it.
You're just a statistic? Yeah. All right, so what do we got to plug in here? This is going to be what? The limit is h goes to 0. What's f of x plus h? Careful. Even easier. What's the value of the function? If I plug anything into this function, what do I get? 10. That's it. Okay. Now, this one looks too easy, but it's true. Why did it work out so easy? Because look at our function. It was a constant function. So what the hell should we get coming out of it? Yeah, okay. So 10 minus 10 last time I checked is 0. 0 divided by anything is 0. And then, so we're taking the limit of 0. And therefore we get what? Yeah. Okay, so if that's true for all values of x, which h? Ah, that h. Is h equal to 0? No, because we're taking a limit as it approaches 0, so it's not actually equal to 0. Oh, this one? Okay, so what does f of x plus h means? It means everywhere I see an x in the formula for f, I need to replace it with x plus h. Do you see any x's right there? So no matter what I plug in, I always get 10 out, right? This one was so stupid it was hard, right? So I just get 10 out, because no matter what I plug in, I get 10 out. That's done, right? Now, this is a constant function, right? So it shouldn't be shocking that, like, it works out kind of easy. But, yeah. Okay. And so we get 0. We all cool with that? Yeah, that's cool. Very cute. All right, so what's our conclusion here? Slope is 0. Okay, so now we have a point, we have a slope. What's the equation of the tangent line? Y minus 10 equals 0 times x plus 3, right? Because that was the slope. All right, so what form did I use here? Yeah, I used point slope form, right? And this is exactly why point slope form is the form we like to use in calculus, because we have a point, we have a slope. Bam, throw it in. Okay. Now, could we rewrite this a little bit? Of course. Okay. And in particular, if if I wanted to graph this, so like if I wanted to throw this thing in Desmos, or if you've got your graphing calculator or whatever, I need it in y equals form, right, as a function. Right now it's not. Okay, but that's easy. I can just move the 10 to the other side, and what's the stuff on the right at this moment? Well, it's 0 times something, so that just disappears. So what we get here is y equals 10. Okay, and so what's the slope of that thing? We already knew it was 0. Does that make sense? Yeah, because what does the original function look like? It's just a horizontal straight line. Well, what do you think the slope of that thing is? 0. Okay, so this question was perhaps maybe a little stupid, in the sense that what's the equation of a tangent line to a straight line? That same straight line, right? Now, if you draw the picture, does that make sense? Yeah? If it's just a straight line? No, it doesn't, Patrick? Well, they'd be right on top of each other. So they would be literally the same line, right? So it's kind of like if I've got my stick here and I put it at some funky slope and I pick a point on it, what's the tangent line through this point that's tangent to this curve? Well, you're looking at it. It's the thing in my hand. Okay, now this is sort of the stupid case though, because it's a straight line. The whole point of calculus is what happens if the curve is all, wiggly biggledy. That's a technical term. Yeah, you better use it on your comps. Yeah, it kind of reminds me. So, having grown up in the South basically my whole life, um, because even Virginia is technically part of the South. Has anybody ever been to a Piggly Wiggly, the grocery store? Anybody ever heard of Piggly Wiggly? Yeah. It was a grocery store chain. I don't think they exist anymore, but you know.
I've never heard of Kroger's till I came here.
Well, yeah, I mean, there is sort of a regional variety of that. There was one other grocery store I remember when we moved to Texas that was kind of crazy. It was called Skaggs Alpha Beta. Like Skaggs, I guess, was some name, and then Alpha Dash Beta. I know it does kind of sound like a fraternity, like Rush Alpha Beta, man. Um, yeah. So, and Kroger. I mean, where the heck did that name come from?
Someone's last name.
Yeah, well, okay, that would make sense, but um, so yeah. Okay, so well, probably not the alpha beta part, but yeah, 100 or what? Skags? Oh, there's still some in Wisconsin? Yeah, no kidding. Oh, wow, that's news to me because last time I checked, Wisconsin is very much not south of the Mason-Dixon line. So, yeah. All right. So, at this moment, do we have any other tools for figuring out the derivative besides the definition? Okay. Now, for this one, if we graphed it, we could kind of look at it and guess that the slope was going to be exactly the slope of the line, right? Okay, so there's maybe one extra tool. But otherwise, do we have any way to do these things to figure out these slopes without doing this definition of the derivative? Sadly, no, not yet. Okay. Now, there will be some shortcuts, which we'll start talking about next time. But, okay. Yeah. Okay. So let's look at number 5 here. Okay. So, fortunately, number 5, do all 3 of those functions look familiar? Hmm? All 3 of those functions are things that we previously worked with on the sheet. Okay, so last time you guys did the second and the third ones up on the boards to figure out their derivatives. Okay, and the first one was from the very first page. So let me just remind you what we got for the formulas for the derivatives. Okay, so if we had, so let me make a table here. Okay, so we've computed all 3 of those derivatives using the limit definition. We did all 3 of them last time. Okay, so for the sake of time, let's just use these results, recycle them, because we've already done the work once, and no need to do it a second time. Okay, now half of you did 1 over x, the other half of you did root x. Okay, so one of the things I would suggest that you do is do, like on your own later today, do the one that you didn't do on Monday and make sure that it works out the same as whoever did it up on the board. Okay, does that make sense? Okay, and then the first one we did together at the beginning last time. Okay, Gucci? Yeah. Now, these are the values of the derivative. What we're interested in are the equations of the tangent lines at x equals 2. Okay? Does that make sense? All right, so take a minute and work out the 3 of these. Okay, so we're going to use the same point for all 3 of them. Okay, now, do we know the point? Kind of. We only really know half the point at this moment, right? We know its x-coordinate. What's its x-coordinate? 2. How do I get the corresponding y-coordinate? What do I need to do? I need to plug into each of the 3 functions and get whatever I get. Okay? What else do I need to know to construct the equation of a line? I need to know slope. So what do I need to plug in to get the slope? I need to plug it in to this guy, right? So the function tells you the y-coordinate, the derivative tells you the slope. Does that make sense? Okay, so plug all these in, and I want 3 equations. Go. This is the part where you either write on paper or hit the chalkboard, right? Since you don't have any paper in front of you. And Broface is just going to sit there. Mm-hmm. Your hair doesn't look quite as unruly as it did yesterday, though. Hmm? Mm. All right, looks like Jaden's nailed it. Let me write them all up down and see if you guys agree. Oh, yeah. Okay, do we agree with all of those things? Okay, the x-coordinates being 2, that was constant for all of them, that was just given. The y-coordinates we plugged into the original function. The slopes we plugged into the derivative, okay, and then we just got whatever we got. Okay, so does that make sense? Right? Now, why was it so quick to do this one? Because we knew the formulas for f prime. What about if we did not know these formulas for f prime? We'd have to go, well, possibly from the left and the right, but we'd have to go through and do that limit definition, right? In order to figure out the derivative formulas. So why were we able to cheat and just immediately write these 3 things down? Because we'd already done them, right? And so we're just recycling work from last time. If we don't know the formulas, we have to actually work them out. And that part is what takes the time, okay? Until you learn the shortcuts, which we'll start talking about on Friday, okay, to speed up the computation of going from here to here without doing a bunch of limit definition stuff. Okay. Now, those of you who've seen some calculus before probably remember these shortcuts. Okay. And so the rule is once we start doing the shortcuts, you can use the shortcuts unless you are explicitly told otherwise. Okay. Does that make sense? Yeah. Okay. All right. So, right. So any questions there? Okay. Now, so maybe two other things to observe here is if I ask you for an equation, like on a written thing or something, am I cool with one of these? Yeah, just leave it, right? And in fact, I like point slope form better because it makes obvious two pieces of information, the point and the slope, right? It makes it real easy to see, do you have the correct point? Yes or no. Do you have the correct slope? Yes or no. And if one of those is incorrect, it makes it easier for me to figure out where the mistake happened. More likely than not, what'll happen is you'll make the mistake on the slope part, but not the point part. Okay. That just, that makes sense. Okay, there's one other thing to observe here, which is this is the first answer that I can remember in a while that's had square rooty stuff in it. How many of you guys look at this and like the hair on the back of your neck stands up? Okay, did anybody have like a high school teacher that all got, you know, all up in your business if you had square roots and denominators? You had a chill teacher?
I think mine brought up that's the whole point. It used to not be accepted.
Yeah. Do I care about square roots in the denominator? Believe me, we got bigger fish to fry, gentlemen. Square root and denominator, square root and numerator, everybody gets a square root. You get a square root, you get a square root, right? I don't care. Okay. Now, that said, if you wanted to get it out of the denominator for some reason, what's the trick? Well, okay, you do that, or you just multiply the top and the bottom by root 2. Because then you'd get root 2 over 4, right? Like, I don't personally care. Square roots in the bottom, square roots in the top, no issue. Okay. But the only reason I mention that is because if I write it one way and you write it the other way, how do you know that our answers are the same? Right? They could look different, even though they're the same number. Okay. So if I multiply that fraction by root 2 over root 2, what is that called? Rationalizing? Yeah. Okay. So yeah, if you want to rationalize, go for it. I'm not going to care. Right? Doesn't matter to me. It's just a number. It's kind of like if there's a pi in it. All right, there's a pi in the answer. Pardon? -1 gentleman coin. So, all right. Question für gutes Fragen? Gucci? All right, see you guys Friday.